Welcome back to another video lesson. This is lesson 9.4 where we are going to be talking about what happens when shapes change their dimensions or the size of the shape changes. You received a purple note sheet in class today. You need to fold that like a book and put it into page 93. My table of contents will just be the title, Changes in Dimensions. Go ahead and get that ready. On the cover of our notes, there's not anything to fill in, but there are going to be things to circle and underline and note as we go through this. We have a triangle here, and if we were to change the dimensions, we would have either a smaller or a bigger, I chose smaller, triangle. And what we now have created are similar triangles. When shapes are the same shape, they're just different sizes, we call those similar figures. So I have a triangle. I started with one that's a little bit bigger, and then I maybe cut each length in half to get this one. And there's a cool relationship that happens when you change dimensions. And you have to understand something called corresponding sides. What I mean by corresponding sides is that this bottom of the right triangle is the corresponding side of this bottom. So it's the same part of the triangle with just respects to the big one and the small one. Similarly, the diagonal that's across from the right angle, this corresponding side would match the small triangle's diagonal as well. So it's looking at the differences in dimensions and then noticing what happens when you're dealing with perimeter. We'll do that first, and then we'll move on to area. So let's look at the front of our notes for a minute. So here we have two isosceles triangles, not right triangles, and you can actually see the lengths around each triangle. So figure A, figure B. If the dimensions of a polygon are multiplied by x, I want you to underline multiplied by x, meaning I'm going to take this figure and I'm going to multiply all the sides by 2, or I'm going to multiply all the sides and make it bigger. I'm going to triple this figure. And then voila, I have a big one. That's what it's talking about. Now let's talk about what happens to the perimeter. So I have a figure. I'm going to multiply all the sides by, say, 2. What's going to happen to the perimeter? The perimeter changes by that same number. So I want you to underline by a factor of x. So we have x here and x here. Those are the same letters, meaning that if we have the dimension, this length doubled, the perimeter of the entire shape will also be doubled. So if you look at the bottom of this triangle, I want you to put a box around this too. The corresponding side, the bottom of the bigger triangle, is 4. It's actually related to our in and out function table that we were dealing with. So if we have a 2, it goes to a 4. Circle this right-hand side, I know they're both the same, and then circle the corresponding right-hand side of the bigger triangle. It goes from a 3 to a 6. Do you see that there's the same increase? You can multiply 2 times 2 to get 4. You can also multiply 3 to get 6. That's what it means by multiplying by a number, by 2 in this case. So the dimensions of the small triangle are multiplied by 2, underline that, to get or produce the dimensions in figure B. That's the pattern. Remember from chapter 8, we talked about patterns, ins and outs. So the corresponding sides we have to look at to determine what the pattern is. Now let's talk about the perimeter. The perimeter, we could add up 6, 2, and we would get a perimeter of 8. We could add up 6, 6, and 4 and get 16. What the cool thing is that the relationship down here, I want you to circle this 8, is the same relationship of multiplying by 2 that we saw with the sides. So the side is being multiplied by 2 to get the bigger shape. We can take the perimeter and also multiply it by 2 and get the new perimeter of figure B. That is the P. So I want you to put a box around this multiplied by 2. If you're multiplying by 2 up here to get the dimensions, we're also going to multiply by 2 to get the new perimeter. So let's go on the inside and just talk about perimeter. There are 2 examples dealing with perimeter on the left-hand side, and then we'll go back to the front and talk about area. So here we have a shape. It's a parallelogram, and suppose the side lengths, 4 and 3, at the right, are tripled. What effect would this have on the perimeter? And we have to do what's called justification, or justify our answer. Our work that we're going to do is part of that justification, and then we need a wrap-up sentence at the end. First thing we're going to do is actually sketch out what will the shape look like if the sides are tripled. So somewhere in this space, I'd like you to the best of your ability, draw a parallelogram. It does not have to be bigger than this. The idea is that it's going to be bigger if you're tripling the sides. We don't have to draw this to scale though. So if we were to triple, meaning multiply by 3, each of these side lengths, 4 times 3 is 12, and 3 times 3 is 9. Notice where I put the numbers. You have to put them in the corresponding spots, meaning the 4 is on the bottom of the shape, it's on the bottom, 12 on the bottom of this one, 3 is on the right-hand side, 9 is also on the right-hand side. And we'll put the label on here to be accurate. So now we have our visual. What we're going to do next to explain what's going on is actually find the original shape's perimeter and the new shape's perimeter. And we're going to actually call them original and new. So the original perimeter, you could add 4, 4, 3, and 3, or you can double the 4, because remember, these parts of the parallelogram are the same length, and then double the right and left. Up to you. Either way, we get a perimeter of 14 inches. Remember, this is just perimeter. We're not dealing with area, so it's just the unit of inches. Now let's talk about the new perimeter underneath. And we're just going to look at our new shape and do the same thing to calculate the perimeter. We're going to take 2 12s and add it to 2 side lengths that are 9. When we do that, we have 42 inches that the new perimeter is. Now we get to compare the 2 numbers. Because we have all of the side lengths, we can compare. Sometimes we won't be given all the side lengths, we'll just be given one corresponding side, and we'll have to just talk about the perimeter. But in this case, we can compare 42 and 14. To compare, we're going to see what the relationship is between 42 and 14. Knowing what we just went over on the front cover, it should be the same relationship as what we had to do to get from 4 to 12. So I should be able to take 14 and multiply it by 3 to get 42. Let's check by doing the division. 42 divided by 14 should be 3. 14 times 3 is 42, so that's the comparison. Now we can make a statement about the effect on the perimeter. If you triple all the sides, the perimeter will also be tripled or multiplied by 3. So that's the last piece of this. I'm going to write my statement up here, and it's almost like a conclusion. So I'm going to start these with the word so. All of this work is our justification. So now we can say our last statement. So the perimeter of the new shape is 3 times bigger than the original figure. So to recap, we drew a picture, we figured out the new and old perimeters, or original and new perimeters, we compared the numbers to see what was going on, then we made a statement about the effect of the perimeter based on that dimension change. Let's do the second one together. Suppose the side lengths of the trapezoid at the right are multiplied by half. Now it's like taking a shape that's a bigger shape, cutting everything in half, and winding up with a smaller one. So that's what's going on. We're going to be getting a smaller trapezoid now. What effect now would this change have on the perimeter? So let's sketch out our trapezoid. It's going to be a little bit smaller, so we kind of can pretend this is to scale. And we have to cut each number in half. The 14s are going to change to 7. Notice I put them on the corresponding sides, the legs of the trapezoid. The 24 is going to be a 12, and then the 13 is just going to be that 6.5. And all of these are centimeters, and now we have our visual. Now it's time to compare the perimeters, just like before. The original perimeter, we have two 14s, so I can condense that by doing 14 times 2, and then I have to add the 24 and the 13. When I do all of that, I end up getting 65 centimeters for the original perimeter. Now I have to do the same thing for the new one. Now I'm going to be doubling 7 and then adding 6.5 and 12. When I add that up, I get 32.5 centimeters. Now I have to compare these two numbers. I'm going to go over here and try to compare them. Remember, it should be the same relationship. I should be able to cut this perimeter in half and get 32.5. So let's try that. What is half of 65, or dividing it by 2? So I've divided this out, and yes, in fact, half of 65 is 32.5. So now I can write my statement. What effect would this cutting everything in half have on the perimeter? It's going to half the perimeter as well. So here's my justification and my conclusion sentence. So the perimeter is half the original perimeter. So you're seeing the pattern hopefully with these two examples. If you manipulate the corresponding sides by either dividing by 2 or multiplying by 3, that same effect, either dividing by 2 or multiplying by 3, is what happens to the perimeter. Let's move on to area next. Now I'm back on the front cover. If the dimensions now of a polygon, so I'm talking about the sides, if the dimensions are multiplied by x, so say I'm going to take this rectangle and I'm going to multiply it by 3, 4, 5. We can find out what that pattern is in a second, but whatever that number is, the area, so like a box area of that same polygon changes by a factor of taking that number that we changed to get the dimensions and squaring it. Because remember, area deals with square units that you can fit inside of a shape. So it's not just the same number anymore, it's that number squared, because we're dealing with area. So let's look at the relationship between the corresponding sides to figure out what x is for this example. So circle 5 and then the 10 because it's the bottom of this rectangle. Then put a box around the 4 and around the 8. Again, if you want to just chart it out, the 5 changes to a 10, the 4 changes to an 8. What's the pattern? Multiplying by 2. So down here, the dimensions are multiplied by 2 to get figure B, to get the new shape. To figure out the area, yeah, you can just multiply. This is 20 and this is 80. What's the relationship between these two numbers? Well, the fun thing is, if you take the pattern, the multiplying by 2, so I want you to circle this, and square it to squared is 4, you can take the old area and multiply it by 4 and get the new area. It's just a cool thing that happens between the relationship of the dimensions and what they change and how it affects the area. So let's try some examples dealing with area. So I'm on the inside now on the right, where we have two final examples dealing with this area change. So the side length of a triangle is multiplied by 5. I want you to underline that or circle that. That's important. What effect would this change have on the area and justify? So we have to write that sentence. So if we're multiplying by 5, the triangle is going to be bigger. So let's sketch out a right triangle. And if we were multiplying each side by 5, that's the pattern. So the corresponding side, here we have 1 centimeter, it's going to be 5 centimeters if we're multiplying each side by 5. The 2 centimeters is going to change to 10 centimeters. So we have a bigger triangle. Here are the dimensions. Now let's just find the area of each. The original area first. We're going to plug in our base and our height. Remember, this right angle symbol tells us that the base is 2 and the height is 1. Half of 2 is 1, and 1 times 1 is 1. So the area of this small triangle is 1 centimeter squared. Now let's do the new area. The base is 10 and the height is 5 for our new triangle. Half of 10 is 5. I'm going to show that. And then 5 times 5 gives us the new area of 25 inches squared. So now we have to compare the 1 to the 25. How could I change the 1, or what could I multiply it by to get 25? Well, I could multiply it by 25. What is interesting about this number 25 is that we could also take the change, the fact that we multiplied each number by 5, and we can square 5, and we will get our 25. That leads us to our conclusion. So the area is 5 squared, or 25 times greater than the original figure. So the only change here is that we are not just using the 5, we have to square the 5, and that will be the change in area. So this last one is a little bit harder because they're not asking us to actually find the area, thankfully, of a stop sign, because we have to do some fancy deconstruction in order to do that with what we know. The stop sign is in the shape of a regular octagon, and sign A, shown at the right, has an area of 309 square inches. We want to know the area of sign B, but the only thing they give us are these two corresponding sides, and that's all that we need because of what we've learned of what happens when we have change in dimension and how it affects area. So let's walk through this one. We're going to look at the relationship or the pattern. What's going on? How do we get from 8 to 12? So we're going to compare first the lengths of 8 and 12. In order to do that, I'm going to see what could I multiply 8 by to get 12. And it's not going to work out perfectly, so I'm going to have my decimal in there. And I'm realizing that if I take 8 and I multiply it by 1.5, I will get 12. Regular octagon means all the sides are the same. We could deconstruct this and find the area of the octagon. I'm not going to, because I know right away that the side of B is 1.5 times greater. That's part of my justification now. So the side of B, figure B, is 1.5 times greater than a side of figure A. That's what we just learned. The relationship between these corresponding sides multiplied by 1.5, you'll get there. Therefore, this is our conclusion. The area of the new figure, figure B, will be that 1.5 squared times bigger times the area of figure A. So we're going to take the 309 and we're going to multiply it by 1.5 squared. Let's figure out 1.5 squared first. You can grab a calculator, take 1.5 times 1.5, or use the exponent key. When we do this, we realize that it's 2.25, and when we multiply 309 by this, we get the new area of 695 and 25/100 inches squared. So a lot of justification, a lot of work to show a conclusion, and we're writing sentences and talking about changes in dimensions tomorrow. Look forward to seeing you then. Have a great night. Goodbye.